But what we're really doing is trying to explore some of the implications that this has for policy and what some of the possible solutions to managing this are. Let's see if I can actually advance the slides. There we go. So two main things I want to get across in the next few minutes. One is that, perhaps slightly counterintuitively, there's no simple trade-off between the amount of energy that we get from tidal energy and the environmental impact that it has. Certainly the two are related, but it's not a simple choice of scaling between one and the other. And because of that, we're going to need strategic planning to get the most energy we can for a given level of impact, or to get the minimum level of impact for a given level of electricity generation. And the second thing is that tidal farms are going to affect each other. And if we have tidal farms owned by different companies in proximity, that means we have some issues around coordination and liability that we have to think about. A note here that we're not talking about barrages, we are purely talking about tidal stream turbines of the type in the picture. And also that this stuff doesn't really matter yet. When we're putting one machine in the water, or even 10 machines in the water, the effects are small enough and local enough that it's not going to have any far-field consequences in most locations. When we start talking about hundreds or thousands of turbines, then this stuff is going to matter. And if we ever want tidal energy to be important or to be significant at a utility scale or a grid scale, rather than purely being for isolated communities, for example, then at some point we do have to scale up to that kind of level. So this is thinking ahead to what we're going to have to consider when that happens. And all the time today, when I'm talking about environmental impact, what I'm talking about is changes we're making to the flow. And that's maybe not directly of concern to many people, but when you do change the flow, that's going to have an impact on benthic habitats through changes in the bed stress. It has effects on any species that use drifting of larvae to reproduce and to disperse. Potentially alters predator-prey relationships simply from having fast flows in different places at different times. So it does have ecological impacts, but I'm not exploring them here. I'm purely talking about changes to the flow itself. So going back to basics, and this will be revision for many people here, when we put a tidal energy farm in a channel, here's a cartoon channel on the right, and we've put a tidal farm marked A across about half of it. And this is a big tidal farm. It's having significant effects on the flow around it. And energy is being lost from the flow in three places. It's being lost at A, at the turbines themselves. So that's the whole point. We're removing energy there to turn it into electricity. So that much is certainly unavoidable. But we all know intuitively that when you put an object or a blockage into a flow of water, the water would tend to go around it. And a tidal farm is a partial blockage. So the amount of water going through A when these turbines are present is less than it would have been when the turbines were not there. And so, that water that's not going through A is instead diverting around A and going on the other side of the river. And as it does that, because it's being forced into a smaller space, it has to accelerate. So the water is flowing faster than it was. And that means there's more seabed drag than there was, and more energy being lost on the seabed, which I've marked here as B. And that's energy which is being lost from the flow as a consequence of the presence of the turbines, but it's not available for the turbines to capture. Then when we go downstream a little bit, we have our fast flow on the, in this case, the right-hand side of the channel, and we have our relatively slow flow on the left in the wake of the turbines. And these are going to mix. The fast and the slow are going to merge with each other. And as they do that, there will be turbulence marked as C, and there's more energy being lost in that turbulence, which again exists as a consequence of the turbines, but is not available to be captured by them. So far, I guess, so unsurprising. We know we can never capture all the energy in the, we know we're never fully efficient with any energy system. But the point is, we've got A, which can be at least partly converted to electricity. We've got B and C that can't, but the ratio between them is not fixed. It depends very much on the layout and design of the tidal farms and the geometry of the channels and so forth. And this is where it becomes important to plan things. And I'm going to demonstrate this with a bit of a cartoon that I need to acknowledge David Wolf showed something very similar a few years ago at IMA, making much the same point. If we have an example channel here with a nice strong tidal flow going from left to right. And this channel has 2 islands in it. And a developer comes along and decides, I want to install a tidal farm north of island number 1, which is our red dashed line there. And they've done their homework, so they know they're going to get a bit less flow through that area than they thought. And that's all fine. They've calculated they can still make a profit. And so some of the flow in that area is being diverted south of that island. So far, so good. Now along comes another developer, and this guy's a bit naive. And this guy says, well, I want to build near the second island for whatever reason. Maybe there's a better grid connection there. And I've noticed there's a faster flow to the south of the island than to the north. So I'm going to put my tidal farm to the south of this island. And he puts that in there. And at this point, we've kind of got the worst possible outcome, in that there's not much water going through the tidal farms. We're not making a lot of tidal farms and causing environmental impacts. So we've ended up with about the worst case. I'm being told my internet connection is unstable, so I hope you can still see and hear me. Now, if instead there was a level of planning and coordination, then the second tidal farm could have been built the opposite side of the same island. It would look like this. Because, well, it depends on the scenario, but assuming that the water is still going to go through this overall channel somehow, that means that it's still going to behave pretty much as it was. There's no way for it to bypass around the turbines. So by getting it wrong on the top diagram, we've got a little bit of electricity and a large environmental impact. By getting it right, we've got a lot of electricity and probably quite a modest impact. And now, the top is kind of a worst case scenario, and no one's going to be quite that stupid because developers will model ahead and look at the effects that their installation is going to have. But in a more complex scenario with more than 2 farms, they're not necessarily able to take account of what other farms might be built in the future. So getting it right requires some sort of overall strategic planning. And this has been demonstrated to some extent by numerical modelling that colleagues at Marine Scotland did a few years back. The figure on the right is showing with its colours the change in the tidal amplitude from putting a lot of tidal turbines into the Pentland Firth. And both of these scenarios generate a mean power of 1.4 gigawatts, but using very different numbers of turbines in very different layouts. The turbines themselves aren't shown here. The point I'm making is they both generate the same mean power. The one on the right is probably causing flooding in Stromness, and the one on the left isn't. So once again, if we get it right, lots of power, modest impact. Get it wrong, a little bit of power and lots of impacts. So we need to make sure we're planning ahead to get these things right. Second point to make here is that tidal arrays affect each other, and that's no great surprise given what we just talked about, because we've shown that the tidal arrays can affect the parts of the channel that they don't occupy. So if there's another tidal array in the other part of the channel, of course, they affect each other. And we've shown 3 kind of template scenarios here, and most real situations will break down into some combination of these 3. The first is straightforward and obvious. It's an upstream downstream scenario. It's partially, although not fully, analogous to hydro on a river, in that if there's a second farm, then both of them get less than if there was just one by itself. B and C are a little bit different, and this is something that's quite unusual for tidal power, that A and B depend upon one another, because each of them stops the flow from diverting around the other one. So if B stops generating, then A loses out because there'll be less water going through A. Diagram C is very much the same as diagram B, except that there's an island present, and the island may or may not make a difference depending on the geometry in terms of how much this diversion happens. But broadly speaking, they're a very similar scenario. And this has again been tested and demonstrated with numerical modelling. This is some work that was done in Oxford quite a few years ago now. And if you look on the left, again, we're looking at the Pentland Firth, zoomed in a bit, and they tried putting simulated tidal farms in these 5 locations marked A to E. And they tried putting them individually and also in combinations. And the table on the right is showing the results, and I'll talk you through a few of the figures here. if we look in the column that's marked B, we can see that B refers to the tidal farm in the inner sound on the south side of this channel. When B is used by itself, it can generate up to 122 megawatts in this simulation. When B, C, and D are all used together, then B by itself at that point, sorry, when B, C, and D are all used together, then B then is generating 320 megawatts. So it's benefiting from the presence of C and D, which are preventing there being an easy route for the flow to divert around B. Similarly for C and D, excuse me, you see C by itself is about 1.4 gigawatts. C with all the others operating is 2.4 gigawatts. So it's a massive difference. D is even bigger. D almost triples when you add B and C in there. This is kind of a maximum possible effect because Draper et al. Were looking for the maximum possible level of generation from these farms, regardless of economics or environmental considerations. E is a bit different. E is much more like the upstream-downstream scenario that we considered, and that's reflected here. We can see E by itself is able to get 325 megawatts, but as soon as you start running any others at the same time, then E gets less power. So this numerical modeling is showing results that match the intuitive ideas on the previous page. And this has all sorts of fun implications when these farms are owned by different people. So in the upstream downstream case, farm A is quite happily sitting here generating away. I just got a notification in the chat. Do I need to read that?
Hi Simon, don't worry about the chat. I'll deal with that.
No problem. That's not quite a co-author, but a colleague of one of my co-authors. And yes, but he's right. This is a 3D, not a 2D problem. This also applies in 2D, but we do have to model it in 3D to get the right results. So in the case of A, he's sitting there quite happily generating. Then B comes along and builds another tidal farm in the same channel. So is there any redress here? Because A is now making less money. Maybe A is no longer financially viable. Does B have any liability for this? In the case of side-by-side generation, A and B are quite happily sitting there making plenty of profit each, and then B stops working, and suddenly A is making less money. So is B liable for their non-performance? Maybe they're having big reliability problems, or maybe B was planned and actually wasn't built in the end, leaving A high and dry. Similarly, in this side-by-side case, when B stopped generating, a lot of the flow that would have gone through A is diverted to B. So A's environmental impact has suddenly increased, which makes me question how meaningful is the EIA for an individual large tidal farm if it's not taking into account all the other farms that are going to be built around it. The last point I want to make here is there's potential for a tragedy of the commons type scenario. I'm sorry about my phone. So this is some, on the bottom right, this is a table of figures from a group at Imperial. And they were simulating a number of different tidal farms in the same region, so close enough to affect each other, and optimizing for the maximum profit and the maximum power, which translates to the same thing. And they produced two sets of figures here, and the ones on the left outside the brackets are optimizing for the maximum power for that individual farm, while the ones on the right are optimizing for the maximum power for the region as a whole. And the thing to note is the figures on the left are always greater. So that suggests that in this setup, any individual farm could generate more than it is supposed to generate greater profits for that one farm at the expense of the rest of the region. And in the classic tragedy of the common sense, of course, if they all do that, everyone ends up worse off. So that's a problem. Potentially, at least a problem. And to some extent that will be dealt with by consenting, what's the word? Conditions, consenting conditions, but they'll tend to be on the capacity, the maximum capacity of the farms rather than how much average energy they're allowed to extract. So we had to think about how to deal with this. And in an ideal world, we want four things out of a management approach. We need strategic holistic planning, for reasons we've already demonstrated. And we also need forward visibility, which is almost but not quite the same. in that somebody building farm A needs to understand what else is going to come along in the future, not just for the same reasons as the holistic planning, but also because there's been work showing that the optimum design of any one farm, including its layout and including the actual shape of its blades, will be different depending on the overall blockage of the channel. So the presence or absence of other farms might affect the design of one that's being built. Third, we need to a way of discouraging people from producing more than they're supposed to avoid that tragedy of the commons situation. And we need a way of dealing with farms that are meant to be built and meant to be operating that are not built or don't operate, so underproduce, and hence have detrimental effects on others. I'm not advancing my slides here. There we go. So there's a table that we are going to fill in the next couple of minutes. There are 3 approaches to this that we looked at, and these are not the only approaches by any means. These are simply 3 examples that kind of encompass a spectrum on the amount of intervention involved. And the first one is prioritizing the free market, and that's pretty much the status quo. On land, if you have a lease to a bit of land, then normally that lease would include the right to the benefit stream of the resources on that land. Now at sea, we can't see any of the current Crown Estate lease agreements, they're all commercially confidential, but we did get to look at an early example one that they published, and it made no mention of access to resources. So as far as we can tell at the moment, that's unprotected, and if I have a lease from the Crown Estate, there is no guarantee that it will always have the same resources that it has when I take out that lease option. If we have detrimental relationships between tidal farms, potentially there's resource to a claim of nuisance, and that's something that's been tested on land. In America, there's been a claim of nuisance upheld against a neighbor for reducing the amount of light falling on someone's land when that was being used for solar power. So that might be a route to dealing with detrimental relationships. But when we have beneficial relationships where farms are depending on each other, it's very hard to imagine somebody succeeding with a claim of nuisance for somebody else not doing something, such as operating a tidal farm. Obviously, a free market approach gives no holistic planning and no forward visibility. And there's little to prevent people extracting too much energy, depending on the consenting and the monitoring arrangements. So there is a risk of a tragedy of the commons type scenario. And there's, as we said, no compensation for a failure to operate unless that's been agreed by private contractual arrangements between the 2 codependent tidal farms. So there are high project risks under this system. If I build a tidal farm, I don't know if it's still going to be generating as much in 10 years' time because I don't know what other people are going to build. And one way of dealing with that project risk is taking a first come, first served approach. And an example of this is the grid situation in Orkney, where there's limited grid capacity, and the most recent wind farms to connect to the grid are the first ones that are told they have to shut down if there's not enough capacity available. So the principle is that later entrants to the market cannot disadvantage earlier ones, and that does reduce the project risk for the first movers. But it also prevents newer farms connecting, and the newer farms are going to tend to have the more innovative and the more efficient solutions. So that's not great. It also means that you can't build more capacity for a greater total output if doing that will disadvantage the first movers. And one thing we've seen is that prioritizing the total output of the region will tend to mean that individual farms get a little bit less each. So clearly it won't give us the optimal results either. So this way we have no holistic planning and not really any forward visibility. Overproduction is less of a problem because as long as it can be measured in evidence, then a later person coming along is not going to be able to affect an earlier entrant. Again, if you've got 2 farms that depend on each other, that's going to have to be dealt with by private contracts. I've been forgetting to fill in this table, but we get a big row of crosses onto the free market. And on first come, first serve, we get 1 tick. We're not going to have the overproduction problem, but it doesn't do very well with the others. So you can probably guess that the third approach is the one that we like. To explain it, I need to explain a little bit of history of the oil and gas industry. This is going back to fairly early days when people were using nodding donkeys onshore for easy to access oil reserves. But at the time when they were deciding who owns an oil field, the precedent that was looked for looked towards was from something called the law of capture, which comes from wild animals. And traditionally, a wild animal is not owned by anybody until it's captured. And when it's captured, it's then owned by the person who catched it, the person who caught it. And that makes a certain amount of sense. But now imagine an oil field that crosses a boundary. That might be a national boundary, or it might just be the boundary between two different landowners. As soon as it's discovered, while it's in the ground, it's not owned by anybody. When it's been pumped up, it's owned by the person who has pumped it to the surface. So as soon as it's discovered, those two landowners are going to be in a race to extract as much as they can and claim as much of it as they can before the other person does. And that led to bizarre ups and downs in the prices of oil, with gluts happening. And it also led to extracting less of the oil because people were prioritizing speed rather than overall effectiveness. So the oil industry went through a number of different solutions to this. And the one they settled on, which is fairly common now across the world, is called unitisation. And that simply means that one developer operates or coordinates all of the interests in a field on behalf of all the owners or all the countries concerned, in order to maximize the overall yield with a pre-agreed split of the profits. That could translate really nicely to tidal power, in that if you have multiple tidal farms with different owners in an area, then one company could be appointed to manage all of them on behalf of all the owners. But importantly, by having a pre-agreed split of the profits, rather than, or a pre-agreed split of the revenue potentially, rather than having it based on which farm has generated how much, it means they can optimize for the total overall extraction rather than for any one farm to do well. So that gives us our forward planning, or at least it gives us the potential for our forward planning, and gives us the potential for our forward visibility, because everyone has an incentive to work together. The tragedy of the common situation doesn't arise because even the first company doing this would hurt everybody, including themselves. And underproduction will be naturally dealt with because everyone wants to deal with these things as well as they can. So it ticks all our boxes by making sure all the incentives are aligned correctly. And we like this option. It doesn't have to be unitisation. There are certainly other ways of achieving it. You could do it by a heavy level of government involvement, controlling things. There are probably other approaches as well. This is simply one that's been demonstrated to work in a free market environment in oil and gas. But if we do want to optimally exploit what is ultimately a scarce resource, then we do need some kind of interventionist, centrally planned approach. And it would be really good to have that approach, that framework in place before it's needed, before the industry scales up enough for it to matter, rather than scrambling when it's a bit too late. Now, just before I finish, there's a couple of caveats here. And the biggest one is that we don't really know how severe this problem is. The examples that I was showing you earlier from the Draper simulations had massive effects. They were having 50% effects on the generation and hence the revenue of some of the tidal farms in those simulations. But those simulations were assuming that each tidal farm would be designed to generate the maximum possible energy from that location, regardless of economic or environmental effects. And that simply isn't going to happen. So a next step from this probably is to do some simulations using more realistic scenarios that might actually get built, and see what is the effect on the LCOE, and is it really going to be a big deal? It certainly won't be as big a deal as those simulations have indicated. It may well still be significant enough to be concerned about, and that's what we need to check on. The second thing is that, especially if we don't end up following a unitized approach, we're going to need some way to enforce the amount of energy that tidal arrays are removing from the flow, which, as we noted earlier, is going to be more than the amount of electricity they're generating. And doing that is actually not straightforward, and there's some new research needed to really have a reliable way of doing that that one could comfortably use in court. I've got some ideas in both those directions, and if people are interested in collaborating, do please get in touch after this. But with that, thank you very much for coming and listening. Thank you in particular to my co-authors who are listed there. In particular, I'll pull out Stephanie Weir here, who was a PhD student with Heriot Watt at the time, and who came up with most of the content here about the policy aspects of potential management solutions. Thank you to all the co-authors and the funders. You're welcome to get in touch with me by email there. And if you want to know more The paper about this was published in Marine Policy last year. It's only 5 pages long and it's in fairly straightforward language. You can click on that to see it if you have subscription to Marine Policy. If you don't, then just drop me an email and I'm very happy to send a copy out. Thank you very much.
Great, thank you, Simon. That was really interesting, and it's great to see actually how the arrays interact rather than what I would think is install loads as much as possible and then just get as much energy. And it's actually really interesting to see how that all works as a dynamic together. We've already received a few questions through the Q&A. So if you have a question, please submit it either at the box at the bottom, or as you can do, as someone else already has, you can raise a hand and I'm able to unmute you and you can ask Simon a question. So what I'm going to do first is unmute Alejandro to allow to talk.
Emma, sorry, Hannah.
Yep.
Could I try turning my video on again now?
Yeah, absolutely. Yeah. Go for it.
I can't. You have to let me.
Oh.
There we go. There we go.
Great. I believe Alejandro should be unmuted. So if you wish to ask a question.
Yeah. Hi, Simon. How are you doing?
Hi, I'm pretty good, thanks. Hope everyone's well up there.
Yeah. Great. Thanks very much for your talk. That was very interesting. Thank you. I just wanted to make a little comment, just to say that some of the issues you've been talking about have been in the mind of developers and regulators for quite some time. Because I just wanted to mention something I was involved in 2012. That was run by the Crown Estate at the time. I guess now it would be part of the remit of Crown Estate Scotland. At that time, it was just the Crown Estate. And there was something called the Marine Modelling Enabling Action Project. And that was a modelling project that included a whole pile of developers and the Crown Estate. And it was run by DHI in Denmark. And basically, they were doing some modeling to see how each individual array would affect each other. And I think they had an arrangement whereby non-development would be able to affect the others by more than 5%. And I don't know how they came up with that figure. But just to say that, you know, some of these things have been thought about for a very long time. I can't remember the outcome of the project, so I don't know if they came to a solution. But just as a bit of background.
Thank you. I was vaguely aware of that project having existed, but I don't know much detail about it. I'd also heard that 5% figure, and I'd heard that it might be written into the leases, but I'm not sure, and I've not been able to see any of the actual current leases. It begs the question, of course, of how do you measure that? I think the conclusion was of that exercise was that the leases that were planned at that time in round one were not going to have any effects on each other. And I don't know whether it ever got any further than that.
Okay, the next person with their hand up is David Patterson, so I'm just going to allow him to talk.
Hi, Simon, can you hear me?
I can indeed. Hi, David. Dan Parsons asked me to say hi.
Oh, well, say hi back. Well, it's a double question. I put it into the QA. When you place the arrays, there's the other consequence, which is to do with perhaps migration of animals, etc., or the removal of energy from the system, which could affect things like onshore seaweed populations or sub-seaweed populations, such as kelp beds, etc. So given that in many areas we're trying to move towards more holistic approaches, is that part of the thinking?
It probably should be. And you mentioned in the written question about organisms having to pass through the turbines. So yes, in reality, while in some respects the optimum solution might be a continuous fence of turbines across a channel, in reality, most of the time that won't be practical for allowing organisms to pass and also for allowing navigation of ships. So it's very much a current research area where people are looking at the optimum ways to design channels where we can't simply cover them in turbines. And that is being looked at present. There's quite a lot of work on it. The kelp question is quite an interesting one because something that people have talked about is whether kelp could be used strategically to actually increase the drag in the places that we don't have turbines, which would lessen the impact of having an unimpeded route for the water to bypass them. So that answered the question. It was a little bit vague, sorry.
No, I think it does. It suggests that we still need to do some work to approach it in a fully holistic manner. And
yes, I would totally agree with that.
Yeah, and there's a lot of research we can still do in trying to put these things together. No, thank you very much.
I agree with that, and I'd also say that that research is only worthwhile if we're able to use some level of strategic planning.
Agreed, yeah.
Okay, great. I don't have any hands up at the moment, so we'll just move on to those that have been submitted through the Q&A box at the bottom. So seeing as David's question has been answered, we'll move on to the next by Clive Fox. How do you think the relative costs and benefits of tidal stream versus offshore wind turbines compare? Thinking of things like more predictable power, tidal, but cheaper and easier technology like wind. Given this, will tidal stream ever really become significant?
That's an interesting question. I'll answer the last part first. Tidal stream, I think, is never going to be globally significant in the same way that some other technologies can be. And that's simply because there isn't enough of it. The total power input to the tides from the sun and the moon is somewhere between 3 and 4 terawatts, which is the same order of magnitude as global electricity consumption. So it's never going to be a dominant force across the world, but it could still be really important for certain countries and certain regions, and Scotland is very much one of those regions. Is it going to become, how is it going to compare with wind is tricky because, of course, offshore wind used to be expensive. And I remember only 7 or 8 years ago, people talking about maybe we can squeeze it down to £100 per megawatt hour. And now there are bids going out at 35, 40 pounds per megawatt hour. So it's really hard to predict how the cost of things are going to change. I don't think tide is ever going to get as cheap as wind, simply because there is more subsea stuff going on. And there's the old slightly jokey adage from oil and gas that doing something offshore costs 10 times as much, doing it under the water costs 100 times as much. It's always going to be a bit more expensive doing stuff under the water than doing stuff above it. But as you've noted yourself, there are advantages like more predictable power. And there are other advantages, certainly in the case of tidal technologies that aren't easily visible. We might get less opposition for building them closer to shore. So I can't answer that. It all depends really on how much the costs come down as we develop. We won't really find that out until we do it, I think.
Mm-hmm. Okay, great. Moving on to our next question. Is there any indication of how much energy it is acceptable to remove from the system? What would be considered an unacceptable unenvironmental impact?
That's the million-dollar question. The trouble is, the answer to it is probably more a political one than a scientific one. You've got to define acceptable. At the moment, I guess you're defining good environmental status and so forth. And there's been some work, including some by Alejandro, looking at all the bits of legislation that would apply to this. But this is not my area, but I think it all still comes down to somebody having to make a judgment on what is an acceptable impact. And I don't know if there's any clearly defined way to do that at the moment.
Okay. The next question is, as you've stated, the change in flow will have environmental effects. It may very well be that the optimization may be completely different once you take into account the effects on species. How would you recommend bringing those changes into LCOE?
Thank you, Beth. I think thank you anyway. That all comes down to whether you're going to try and put a monetary value on ecology and on species, doesn't it? And some people would certainly say that's the way to do it. And some people would say that maybe you don't try and bring those into the costs, you treat them separately. I don't know. Certainly when we're trying to decide what a acceptable environmental impact is, we're going to have to potentially weigh up different environmental impacts that apply to different species. I definitely don't consider myself qualified to try and comment on that any further.
Okay, we've got 2 more questions left. From a layman's point of view, I was wondering whether A and C from your scenario shown where the energy between low and the high channels swelled in your first scenario would work.
But if you can clarify the question at all, Claire, what you mean by whether it would work.
I think Claire is still in this, so hopefully it will get. Oh, sorry, she's just put into the Q&A. Sorry, I mean at building at C.
Ah, okay. So adding a third tidal array where the partially in the wake of A and partially in the flow going around A. I think that would be a bad place to build a tidal array, because we know that's a place with high turbulence, and generally turbines don't like turbulent flow. So there certainly has been quite a bit of work where people have looked at layouts where people recognize you're going to get an accelerated flow around a tidal farm. Or more people have more often done it looking at the layout of individual turbines in a farm, but it applies at different scales. You recognize you're going to get an accelerated flow around a turbine and through the gaps between turbines. So there's been work certainly on array layouts looking at taking advantage of that acceleration by putting another turbine just downstream to capture it. And certainly that could be applied at array scale as well as at individual turbine scale. You probably wouldn't want to put it half in and half out of that bypass flow, because you'd just be giving yourself extra turbulence.
I see. And the last question that was written in the Q&A box, if anyone has any other questions, please submit them there, is from Beth as well. Again, will floating tidal be the future due to lower O and M? I have to admit, I'm not sure what O and M is, so if you could answer that, that would be really great.
Sure. So O and M for other people is operations and maintenance. So the idea is that floating turbines may have, or probably do have, lower maintenance costs than ones that are fixed on the seabed, because you don't need such a big vessel with such a big crane to get to them. Will they be the future is, I guess, literally the million-dollar question, and then some. The companies that are building them certainly think so, and the companies that are going for the seabed-mounted ones presumably disagree. Time will tell.
Okay, we don't have any other questions left to answer that have been submitted through the Q&A. This whole session has been recorded, so any answers that we have discussed, you can rewatch if you want. And your email address was given on your very final slide, wasn't it, Simon, if anyone wants to get in contact?
I'll drop it in the chat now just in case as well.
Yeah, that's great, thank you. And that just leaves me to say thank you, Simon, for being our second presenter for the MASTS webinar. It was really informative, and I hope that everyone agrees. And just to let everyone know, we are got plenty of other talks coming up in the next coming weeks. So please use the same registration link that you did if you are interested in any of the other talks coming up. And that's it. Thank you very much.
Thank you, Hannah.